Hey Chemistry, Mrs. KJ here, going over 3.12 Review Metalloids and Intertransition Metals. Review concepts presented in the lessons metalloids and intertransition metals. Metalloids, including the silicon found in sand, are located on the periodic table between metals and nonmetals and share properties with both. The intertransition metals, which have unique properties, include many elements that do not exist in nature. Goals for this lesson: review the two previous lessons. You can download the study guide if you like. Key concepts in metalloids. Metalloids are located between the metals and nonmetals on the periodic table. So right in here. Metalloids share properties with both metals and nonmetals and display their own unique properties. Remember, they're kind of. Oid meaning kind of. They're kind of like metals, kind of like nonmetals. They're in between. Some metalloids have applications in computers, transistors, and microchips. Periodic table groups some elements as metalloids. Properties: they may be shiny or dull, somewhat malleable, somewhat ductile, conduct heat and electricity, somewhat, and located in the spheres between the metals and nonmetals. So again, often we call this shape the stair step, and those are our metalloids. Key concepts in intertransition metals. The intertransition metals are located in two series at the bottom of the periodic table. The intertransition metals are split into two series, the lanthanide and actinide series. Most of the actinides do not exist in nature. They are only made in laboratories and are all radioactive. The lanthanide includes some elements that are relatively common on Earth and others that are rare. Alright, and radioactive, remember that means the nucleus is going to break down and emit particles or electromagnetic waves. So stuff, particles, is going to come out of it, or electromagnetic waves such as gamma rays, X-rays, microwaves, infrared rays, light, the colors of light. So those are examples of electromagnetic waves. Periodic table groups some elements as intertransition metals. Some are radioactive. Many are made in laboratories, so they are not found naturally on Earth. And they are located on the bottom two rows here. So again, we talked about how they actually belong here, but we put them down below the lanthanide and actinide series. I don't know why they call them lanthanide and actinide series instead of lanthanide and actinide rows, possibly because they're technically a part of this row down here, row 6 and row 7. So, organize key concepts. The periodic table, some groups of elements are intertransitions, others are what? Metalloids. They're located in the stairs between metals and nonmetals. They are somewhat ductile. And what's another one of their properties? Somewhat malleable. Intertransition metals, many are made in where? Laboratories. Some are radioactive, such as plutonium and uranium. All right, and we will go ahead and go to our book. So we're going to start out with problem set 25, metalloids. Metalloids, elements that sit in a jagged line on the right side of the periodic table, or a stair-step line, have properties that are similar to those of both metals and nonmetals. Objective: locate metalloids in the periodic table. Discuss some of the properties of metalloids. Metalloids are elements situated between metals and nonmetals, both on the periodic table and in their physical and chemical properties. Remember that metals make up the left and middle and bottom of the periodic table, and nonmetals spread out from the table's top right-hand corner. Dividing those two classes of elements are metalloids, which form a jagged or staircase line between metals and nonmetals that stretches diagonally between groups 3A and 6A. Only 7 elements on the periodic table are metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. Metalloids have some properties that are similar to those of metals, but other properties that are more similar to those of nonmetals. For example, metalloids are solid, like most metals. However, some of them are dull, like nonmetals. Metalloids are malleable and ductile, like metals. They conduct electricity and heat better than nonmetals, but not as well as metals do. And so again, here are 7 metalloids, and all metalloids are solid at room temperature, which we also know from ours because they are not outlined in red, which means it is a gas, or outlined in blue, which means it is a liquid at room temperature. Which metalloids are in the 5th period of the periodic table? Okay, so remember period goes across. So 1, 2, 3, 4, 5. They're asking for the 5th row, which is antimony and tellurium. Describe properties of metalloids. Gold, Au, is a metal. Sulfur, S, is a nonmetal. And boron is a metalloid. Rank these 3 elements from highest to lowest in terms of their electrical conductivity. So hit pause, get your answer. Recall relevant information. Metalloids have properties that fall between those of metals and nonmetals. They conduct electricity and heat far better than nonmetals do, but not as well as metals do. Of these 3 elements, gold is the best electrical conductor because it is the metal. Boron is an intermediate electrical conductor because metalloids are in the middle. And sulfur is the poorest electrical conductor because it is a nonmetal. Tip: metalloids have physical and chemical properties that fall between those of metals and nonmetals. All right. So we'll just do this one. Tell me go ahead and just tell me which ones are metalloids. So hit pause, get your answer, and they are the ones that we have with the background of orange. Those 7 elements right there. Use the periodic table at the back of the book to put the following elements in order from the best conductor of electricity to the poorest conductor of electricity. Selenium, tin, antimony. All right, so which one is going to be the best? Hopefully you know which one is the metal. Which one's the metal? Tin. Tin is a metal. All right, and so now we want to see which one is the metalloid. So if we look at metalloids, that's antimony. So antimony would be in the middle, and that leaves us with selenium, which is a nonmetal, to be the worst or poorest conductor. Which element is probably a better conductor of heat, silicon or phosphorus? Explain your answer. All right, so we have phosphorus and we have silicon. Which one's the better conductor of heat? Hit pause. Answer is silicon would be better because it's a metalloid. It's closer to being a metal. Nonmetals, again, are poor conductors. All right, so let's go to problem set 26, inner transition metals. Objective: locate the inner transition metals on the periodic table, identify the transuranium elements, and describe how they form. The lanthanide and actinide series of elements, which are generally shown at the bottom of the periodic table, have physical and chemical properties that differ from those of other transition metals. And if you're wondering why, you may remember one of the other problem sets that I went over in the book where we talked about how orbitals are not all perfect circles. There's actually the S sphere orbital, the P orbital, which looks like a peanut, the D orbital, which is a daisy, and the F orbital, which is a flower. The lanthanide and actinide series are all F orbitals. So that's what makes them different. It's called the F block, whereas the regular transition metals are only having D orbitals, so they are called the D block. If none of that last paragraph made sense to you, that's okay. You're not going to be tested on it. I was just throwing it out there, so in case you were wondering why they're so different, that's why. If you have questions on that and you want me to explain that further, I would be happy to. Just let me know. All right, back to the book. Look at the periodic table at the back of the book. Notice that 2 rows of elements are separated from the main body of the table. The top row is called the lanthanide series, named after the element lanthanum, and includes elements with atomic numbers 57 through 70. The bottom row is called the actinide series, named after actinium, Ac, and includes elements with atomic numbers 89 through 102. Long ago, the lanthanide and actinides were grouped together with the other transition metals. However, chemists eventually discovered that these inner transition metals have chemical and physical properties that differ from the other transition metals. Many of these elements are so similar to one another that they are difficult to distinguish. So in other words, what they're saying is that californium is so close to berkelium, I'm not sure if I pronounced that right, but it's after Berkeley, that scientists really have to look to tell the difference between them. That's what they're saying. All of the intertransition metals are silvery in color. They are all very shiny, but they tarnish easily in air. All are good conductors of electricity. They all react easily and explosively with nonmetals. However, one major difference separates elements with atomic numbers greater than 92 from the rest of the intertransition metals. These elements, which have atomic numbers greater than that of uranium, are known as the transuranium elements. They do not occur in nature. Transuranium elements are all radioactive, with half-lives significantly shorter than the age of the Earth. Therefore, if they were ever present on our planet, they decayed long ago. Scientists can synthesize these elements using machines such as nuclear reactors and particle accelerators. Okay, let's back up and talk about this couple of sentences real quick. So we don't have them in nature. They're saying that possibly at one point they were on Earth, but because they're radioactive, they're breaking down. The amount of time it takes to break down is called a half-life. Because they break down so quickly, even if there were some at some point, they're all broken down by now, and we have no record of it. And we'll talk more about half-lives next semester. Remember, the lanthanide series includes elements with atomic numbers 57 through 70. You don't need to memorize that because you can just look. 57 through, oh, let's put 71 on there. And actinide 89 to 103. So it does vary a little bit on that last one, depending on apparently what periodic table you're using. As a whole, lanthanide and actinides are called intertransition metals. These elements have very similar properties which differ from those of other transition metals. If you're worried about the fact that it's saying 102 here and it's 103 on our periodic table, I don't think there's any quiz or test questions on that you'll get wrong because of that. If there are, just let me know. Example 1. Use the periodic table to identify intertransition metals. Neodymium occurs naturally as part of several minerals, including xenotime, monazite, and bastnasite. Magnets are made from neodymium, are quite powerful. Is neodymium an intertransition metal? You look down here, it's in the lanthanide series. Yes, it is. Describe the formation of transuranium elements. Which of the following elements is a synthesized element? So synthesized means made, that does not occur naturally on Earth. All right, so can you tell me which ones in general would be the answer to this question? It would be all the ones that are beyond uranium. So these would be man-made, from neptunium all the way down here to number 103. All right. Use the periodic table to identify which of the following elements is an intertransition metal. Again, hopefully you know all your intertransition metals are the ones below the periodic table. So they are all the ones down here. Einsteinium, named after Albert Einstein, does not exist naturally on Earth. Explain how scientists can study Einsteinium even though it does not naturally occur. All right, so hit pause, get your answer. Answer is, scientists use nuclear reactors and particle accelerators to create atoms of the transuranium elements, including Einsteinium, so they can study these elements' properties. And how are the transuranium elements different from most other elements on the periodic table? Answer is, unlike most elements on the periodic table, the transuranium elements do not exist in nature. They are formed in laboratories, so they are man-made. There's other ones that are man-made, like any of the ones that have 3 letters are still in discussion in the scientific community. So you may see that, oh, maybe in the last couple months even, scientists agree that this is an element and it has a new abbreviation. All right, if you have questions, let me know.